that I've said is that basically your project's due in 2 weeks. Please get started on it early. You're going to have questions, and I will not answer questions in the middle of the night. So maybe wait till the night before. I can't help you that much. This is currently how they're making DRAM. They're burying the capacitors down into the substrate. And we'll see if my finger cooperates. They take these little fingers here, and there's actually 3 layers within there. You can see like a green and a pink and a green layer in there. 2 layers are conductive. The inner layer is a dielectric. Having a very thin layer of dielectric between 2 metal layers makes a higher capacitance. Using higher K materials makes a higher capacitance, and making them small. Making the fingers, or I should say, burying them in the substrate, making them long, making the A part of the epsilon A over D big, also increases it. A lot of problems with shorting out. The yield isn't perfect. In order to kind of like overcome that, what they do is they have a way of masking out defective rows and columns and replacing them with some extra rows and columns. And we'll get to that in a chapter or 2.
And so if trench DRAM technology is losing its momentum, then what's replacing it?
This is what's replacing it, is these, they're actually putting the things down in there. There's only so far they can go, and I'm not too sure where they're going to go next. It's to the point it's slowing down their processing shrinkage. Processors are down to about 5 nanometers in production, 3 nanometers in like research mode. Micron, they're still stuck about 9 nanometers because they need that size to actually build the capacitor underneath there. And then there's also heating problems, because you get that many transistors close together, things get warm, you have to refresh faster. I'm working on trying to get someone from Micron to come and talk to this class. We'll see what happens. Maybe I could get someone from TSMC to come talk to this class, or IEEE or something. I've got a meeting with them first week in February.
That'll be fun.
They are hiring. They have plans to hire 300 fresh out engineers this year in Arizona, which means it's going to be harder for everyone else to hire people. The number of job offers you just got has been multiplied by about a factor of 6. That was 0. It's no, never mind. So there is the trench capacitor cross section. We went through that yesterday. We looked at the equilibration circuit yesterday. This is one of the circuits that you're going to need to build for your project. VCC over 2, and don't call it that because it has a slash in it. Call it VCC2 without the slash. Will be an input to your equilibration circuit. EQ will be an input. D and D star will be both inputs and outputs, depending upon what's driving it at the time. And you've got 3 transistors in there. If you're not sure where to, use the transistors in generic 13. Write this down. When you build your project, you're going to have to put your own transistors in. There's a library called generic. I told you I had to write with my finger. 13. And for the NMOS transistor, it's NMOS/NMOS or something like that. Use those transistors because they have model files built into them already. When you go to simulate, if you just use something that looks like a transistor, what you're going to get is you're not going to
Hey,
be.
what's up, brother? Yeah, these are the 2 questions from earlier. I only have 4 minutes.
Okay. Those IO transistors you'll have to build in your project 3. They will be integrated into the sense amp when you put the sense amp in there. And basically all they do is they take the digit lines, DO and DO star. DO star will be coming from a different part of the array. In your 2x2 array, the way you do this is you've got a 2x2. You take D0 from that digit line and you take D0 star from the other column. And you compare those two in your sense amp. So you got the 2 inputs in here. They will be shorted together when this C select is true. So when it goes true, it turns on all these transistors and shorts D0 star into IO star through that transistor, and shorts D0 into IO through that transistor. So that's the basic idea of how those work. And they will be integrated into your sense amp. This is the basic sensing latch. It could be replaced with an op amp, as it has been now. Sorry. Okay. I can do that. What we need for real life is a mute button. Okay. So we've got this, maybe you could mute me. We got the sense amp. We've got the signal that we're sensing D0 coming in. It's going to be a little bit above VD, oh great, VDD2 plus some signal. This is going to be pre-charged to VDD2. I love writing with my finger. Okay, and what we do is we turn on the power supply for the latch. So HCT is going to the PMOS. This is the positive power supply. It's got to go to VDD. Inlet is the negative power supply, so it's going to go to ground when I power this thing up. And basically, it's going to pull this in. This is just 2 back-to-back inverters, so it's going to pull it into one of its 2 stable states. If this is a little bit higher than VDD, if VSIG is positive, I'm going to pull it up to VDD, and if VSIG is negative, I'm going to pull D0 to ground. And it will hold it there, but it has to be powered up for that to happen. All the IO circuits, they clump into and put into the sense amp. So you can see this is a sense amp. It has both the P latches, and it has 2 of those because they're slow and defective because they're PMOS. It has an N latch over here, so that's the N side. It's powered up with NLAT star. These labels are amazingly convenient for reading schematics. You know, that one's going to ACT. The equilibration circuit is that circuit right there. So that is buried in the sense amp. And when you build the sense amp for project 3, this is what it will look like. I've got isolation transistors. My IO transistors are right here. And I've got a second pair of isolation transistors and another equilibration circuit. This is the standard sense amp, and that's what you're going to build for project 3. And then you simulate it for project 4. Okay, so for the rest of that was the review part. For the rest of this class, we're going to look at the review of the review. Something important. Yeah, never mind. We're going to be looking at row decoders, and we're going to look at how some of that works, and the address decode tree and what it takes to bootstrap things up to VCCP. This is the horrible timing diagram. We've got a couple of things going on here. First step right here is we're equilibrating. And what equilibrate means is I'm going to pull the digit lines D0 and D0 star are going to go to VCC2. So I'm going to pre-charge, and I'm going to use as many abbreviations as I can. Pre-charge the digit lines to VCC2. That's the first phase. Now in the second phase, I pull the word line up. And when I pull the word line up, I'm opening the row. That's my RAS. And when I do that, the charge on my M bit is going to get dumped onto the digit line, but it's not enough to pull it all the way up or pull it all the way down. So D0 star goes high a little bit. So word line goes up, the row is open, and D0 is going to go either up or down, depending upon whether it's you have a 0 or a 1 stored. Now this phase right here, you can see NLAT's going down. What else is going up? ACT is going up. So ACT and NLAT turn on the sense amp. The sense amp goes on. And once the sense amp goes on, I start to rail. D0 is going all the way up to VCC. So in this case, I'm reading a 1. Now when C select comes on, column select comes on, I'm reading that data back out. So that's being read back out. And then I'm going to write a value into here. And me and Sean were arguing about this right before class. D0 star, in this case, drops down during the write operation. When does it drop? It drops right after the C select starts to go high. So it looks like what I'm doing is I'm writing a 1 also. Well, I'm writing 1 on D0 star, which probably means I'm writing a, where's D0? D0 is going, where D0 star is the one we're reading out. In this case, you can read from both sides of the sense amp. You can, it just depends upon how you get the things selected. So D0 star is being dropped and it's going back down, and then you go through another cycle. Okay. All right. Where are we going from here? We want to look at the bootstrap driver. There's a NOR driver and a CMOS driver. Now, part of the thing is the word line high voltage has to go to VCCP. And we're going to lose a threshold across the transistors going one way or the other. Since the word line driver has to fit in the pitch of the word line, because I've got to get one right next, I've got a word line here, I've got to get another circuit right in the next word line. So it's got to fit in that very narrow pitch. It may be convenient to actually set this thing up so I don't put any PMOS transistors in it. So I need buffer drivers without PMOS transistors in them. Takes up a lot less space because you get rid of the N wells. The disadvantage is we've got to figure out a way not to lose a threshold across that NMOS transistor on the top. That will be the whole purpose of the bootstrap driver. Okay, And this is called an enhancement load inverter, because notice the transistor on the top is not a PMOS. Because it's not a PMOS, I don't need the end-well. I've saved myself a whole bunch of space. The disadvantage is, we're about ready to see. There's two cases here. If we look at the case where I've got this driven to I've got the gate driven to VCC, and this is, won't be wishful thinking here. Oh no, it says VCC up here. This is at VCC. If this is at VCC, this transistor is on, and my output is going to be pretty close to 0 volts. We're happy with that. The problem is when I put the 0 volts on the gate, this transistor is off. This one's at VCC. What I'm going to get here, because I have to charge the output, I need a small amount of current going through it for the charge. I need at least a threshold voltage drop across this gate to source. So what I get on the output is VCC minus V threshold. That's a problem. I've just killed my noise margin. Now, if I come up with a brilliant idea of driving this gate when this transistor is off, I drive this gate to VCCP, which is greater than VCC plus a threshold. Now, when I get a threshold drop across that transistor, when the top one is on, what I get is VCCP minus V threshold, which hopefully is greater than or equal to VCC. It was really fun doing second order circuits writing with my finger yesterday.
Brings you back to a simpler time of finger painting.
Finger painting, second order differential equations. It all rolls back around. I can handle this. Okay. So this is the enhancement mode inverter. The big difference is this is not PMOS. The transistor on the top is NMOS to save us the space of that N-well. In order to make that thing work though, I've got to drive the gate at a higher voltage to maintain my noise margins. Nothing too complicated yet. Wait till I throw the capacitors in. Yes, the capacitors. What could make this better? Okay. I have a capacitor hanging out in free space, and I magically charge it to 3 volts. It's going to have 3 volts of charge across it, and I notice I just said 3 volts of charge because Q equals CV. So whatever voltage I have across that with a fixed capacitance defines the amount of charge. Now I magically take this capacitor and I move it over here without losing any of the charge across it. This is quite a feat. There's going to be transistors involved in a minute. It's still charged to 3 volts. But now if I put it in series with a capacitor that also has, why won't my finger draw? Also has 3 volts across it. I put this C1 in series with it. What I'm going to see when I do KVL, they're going to add, and I'm going to end up with 6 volts. Now this involved magically moving capacitors without losing any charge across them. The way we're going to do this is we're going to charge both capacitors up with a switch across them. Then we're going to, such as a transistor, and then we're going to throw that switch closed, and suddenly we're going to have 6 volts across the pair. Leave one floating, and one will be at 6 volts. Okay. Anybody screaming so far? Not yet. So let's make it a little bit more complicated. What happens next? Oh, that's 13.
The sun's come out and stopped snowing.
Yes, it has. It's supposed to. Ian doesn't think I'm going to make it down to Phoenix. I got to be down in Phoenix to get my vaccination on Friday. He's seen the pictures about there. He doesn't think I'm going to make it. I go, no, it's going to melt before that. I will make it. And my driveway is clear. I can get out of my driveway. The neighbors can't get out of their driveways, but that's their problem.
Yeah, the snow is perfect snowball fight snow, but it's not great
Yeah.
Building snow.
Yeah,
So
it's pretty light and fluffy, which makes it easier to shovel. Okay, so what I want to do is I want to bootstrap this. Okay, this is bootstrapping part 1. Let me just collect my thoughts here for a second. I've got an enhancement load inverter. That enhancement load inverter, oh, where's my finger painting? Why is it not finger painting for me? Okay, there we go. The enhancement load inverter is M1 and M2. Those are just a inverter that only uses NMOS. And I put this extra, no, I still want to touch. I want my whiteboard back. I put this extra transistor in here, M3. The M3 is a diode connected transistor, and we talked about this in EE490. All it's doing is this transistor has VDS always, VDG always equals 0 because it's got a 0 volts across it. VDS must equal VGS, which if VDS equals VGS, it's always in saturation. And so current is always flowing. What we're going to do is VN is initially at VCC. If it's at VCC, then my output is going to be whatever my V out low is that's associated with this M1 transistor. And my Vx, which is this voltage right here, is going to be, this is at VCC. This is at, the gate's at VCC. So Vx is going to be, I've got a threshold, it's in saturation, so I've got at least a threshold voltage across the gate to source. It's going to be, Vx is going to be at VCC minus a threshold. Okay, let's change colors. Yay. Get out the other paint. I get the black paint on my finger. If I turn VN to 0 volts, so VN gets switched to 0 volts, now this transistor turns off when I'm at 0 volts. My V out, where the heck is VN? VN's right here. VN, because this transistor is on, M3 is on and in saturation, it's going to force V out high. And V out's going to go all the way to VCC. Okay, because it's going from drain to source and not gate to source. I've got VCC here. Now we got to figure out the voltage here at Vx. I don't know what it is, so I'm just going to call it V boot. It's some unknown voltage, V boot. And the next couple of slides, we're going to calculate what V boot is. I haven't lost you guys yet, or at least nobody's complaining. Or you're so lost, you're not complaining. Okay. What is V boot? We're going to start with the assumption that all the current through this capacitor will end up going through this capacitor. This is already charged, so there's not going to be any like current flowing. So the current flowing, yeah, the opposite magnitude, but they should approximately equal each other. Now we know that I equals C dV dt. Oh no, however we're doing with differential equations in this class. So the current through ICS is C dV dt. IC boot is the difference in voltage across it, which is V out minus Vx, the derivative of that with respect to time. I move things around, and so I get all the dV dx's on one side and all the dV out dt's on the other side. And then I integrate it. And I do a little bit better job on the next slide, I think. Nope. I integrate that and I solve for V boot, and I get V boot is VCC minus a threshold plus VCC minus VOL times C boot over CCS minus C boot. So we want C boot to be big, and we can control C boot. It's not a real capacitor. Well, it is a real capacitor. It's not a capacitor that we actually have to build. C boot is the gate to source capacitance of, what was this, M1? We'll call it M1. Is the CGS of M1. So it's already built into my circuit. It's going to be fairly large. All we have to do is make the CCS small, and we should be able to get more voltage out on this boot node than we originally put in.
I wonder if I still remember how to do differential equations. It's been like 2 years since I took DiffyQ.
You have no idea how painful it was coming back to teach. As a working engineer, the most complicated differential equation I ever solved, and I didn't solve it, I'd let Me2 solve it, was I equals C dV dt. That was it. I start homeschooling my son, and somewhere during calculus, we're doing Saxon calculus, we are doing actual differential equations, and I'm like, whoa, I just don't want to do this. And then, even worse yet, I get to NAU, and they tell me I'm going to be teaching 280, and I go, Intro to Electronics, yay, I can handle that. Guess what the first part of that class is?
Differential equations.
So I've learned.
Voting plots.
Then I taught 325.
Well, at least the differential equations aren't until like the very end of 325.
No, it's all differential equations. It's 20 different ways to solve differential equations.
Oh yeah, isn't it?
Yeah. Okay.
Fourier transforms, that's not till the end of 325. That's what it was.
Yeah. Okay. So we've got this bootstrap line driver. what I'm doing here is I'm replacing that diode connected transistor. I've got something driving this. Notice the unknown driver here. When I go across a drain to source, I'm not going to lose a threshold. I lose the threshold going across the gate to source. So I want to charge this node up between VCC minus the threshold and V boot. And when I do that, my driver, this is going to have to be at VCC. This is at, when it turns on, it's going to go to VCCP. And I get a high enough voltage here that when I lose a threshold across this transistor, I'm going to get VCCP out here. All NMOS, so it will fit into my nice little word line pitch, yet without losing a threshold. One extra transistor. And these are actually the gate to source and the drain to source capacitance of this M1 transistor. Okay. It goes up, that goes up. I don't want to talk about that. 15. This is where the second laptop's coming in. I'm using my second laptop as a notebook in this case. Where my notebook usually fits into this. Okay, we got to figure out what is the initial voltage across B1. I've got VCC on the gate, so B1 is going to be at VCC minus a threshold, because I'm going to lose that threshold drop across the gate to source. That gives me my initial voltage. PH, my word line driver thingy up here, the power supply, is going to switch from 0 to VCCP. So I'm turning this driver on. We want to write the KCL equation at this node B1. Well, I've got the current going in. My gazentas equal my gazatas. So my gazenta currents are, if you've missed that, that is the current that goes into the node equals the current that goes out of the node. Going into the node, I have IC, oh great, GD1 is going in. ICGS1 is also going in. I'm just writing a really, see, my finger's not cooperating. Equals, sometimes I write on the screen with my finger and it doesn't write. And what's going out is ICB1. So I've got that equation right there. Current going in equals current going out. We want to use this equation to find the final voltage at B1. That will be our V boot. I equals C dV dt. This is a more complicated equation that I probably couldn't write with my finger. So I take that initial KCL equation and I transform each one of the pieces into the individual C times the dV dt. I get this, I group the dVB1 terms together, I integrate, and I get V boot. V boot is VCC minus a threshold, but it's plus VCCP times this capacitive divider. So I'm getting a higher voltage on V boot on the node here than I would have initially expected because of all that capacitance and the current charging up through it. Okay, we're going to take a 30-second break here so I can go turn the timer off on my oven. I'll be back. This is what happens when I work at home. There. I'm making something for pizza night tomorrow. Okay.
Tonight. Yeah.
And I did not turn the timer off. I have to hit it twice. There it goes. Now it will not beep at me. Okay. Multitasking. Okay, so this is what I want to do. I've got my standard CMOS voltage level, 0 to VCC, coming in on the decode line for this row. So this is row 17. And decode would be decode of 17. It's coming in here. I put the additional transistor in there, series transistor, and now that's acting like the bootstrap driver that's going to modulate B1 between the two levels, and one of them is going to be a higher voltage than VCC because of the charge sharing across the gate to source and the gate to drain capacitor. That gives me a high enough voltage. Phase 0 is going to come in. Phase 0 is going to be 0 to VCCP. And this is going to give me my word line out is going to be going 0 to VCCP. One end extra transistor over a standard driver, and that was the M3 transistor up here. No PMOS, so I can still fit it into a smaller area, and I can get the drive going from 0 to VCCP. That is for that row. Next row, we would use another signal. I don't like some of Keith's terminology, but I get over it. Okay, what we're gonna do here, think about what's going on. This decoder line is initially at VCC. Wait, let me write down. I've got this written down in a well thought out way. Let me read this to you. In region A, decode is low and decode star is high. So this side of the M3 pass transistor is low. This is low and B1 is low. And we're seeing that in region A. B1 is low. The next thing that happens is decode goes high. And you can see this little dotted line here on the decode signal starting to go up in the region between phase A and phase B. B1 initially gets charged to VCC minus a threshold. And this is all written out in my slide solutions too. M1, B1 is a high enough voltage. This is this B1 right here. It goes to VCC minus a threshold. It's a high enough voltage to turn M1 on. Then my phase 0 starts to go up. So as phase 0 gets pulled high, and phase 0 is kind of like the signal that's going to generate word line 0. word line 0 goes up also. When phase 0 and word line goes up, that bootstrapping thing in here pulls B1 up all the way to V boot, but it takes the word line driver being on before that happens. Wow. Okay, goes high, pulls up B1, and so it can maintain the VGS on the M1 transistor. In region D, phase 0 pulls low, which pulls word line 0 low, and B1 starts to drop back down to a lower level. So then B1 drops down when these two turn off, and you can see it dropping right about there. Then DEC turns off, the decoder turns off. Where's the decoder here? It's probably this one right here. The decoder turns off, and as the decoder turns off, B1 goes back down to its low value. So you can see the bootstrap working. It's actually the word line voltage and the phase voltage. The drain and the source voltage of that transistor is pulling the gate voltage up a little bit. It's pulling it up to V boot. Because it's trying to maintain the VGS. VD goes up, VS goes up, VG goes up to maintain the VGS to keep a constant current through that transistor, is the way I would have thought about it. Charge sharing works too. Okay, so this is how I build the circuit. This is called a donut gate. And it's called a donut gate because you can see right there, it says donut gate. It's completely surrounding. I've got decode coming in here. Decode is the drain of the transistor. So this is the drain. Finger, don't fail me now. The gate is going to VCC. So this is the poly gate region right here. This is the gate. This must be M3. So this one is M3. And the source is this side of it right here. The source is going into the gate of M1. And this must be M2. Okay. We want to minimize the B1 capacitance. Remember, we wanted that B1 bootstrap capacitor to be smaller to maximize the charge sharing. We can minimize the capacitance using a donut gate. Okay, there'll be a quiz on this later. Donuts, pizzas. What's the
Donut gate, pizza gate.
What's the universal donut?
We just need a pasta gate.
What?
Pasta gate.
Mm-hmm. Okay. And we are behind. It says 2020. A lot of times when I'm writing the year 2021, this is what I actually write. Oh, where's my finger? 2021. It's a 5-digit number, so no.
Well, plus one.
Yeah, 2021. So this is chapter 2. This is the meat of a lot of what you need for the projects and for the midterm exam in this course. So it's a good to spend time on the pre-lecture quizzes now. If you don't know everything about the column decoder and everything, you'll survive. But you need to understand this material to be able to do the project. And we'll go through it again in more detail, and I will help you with the projects. we looked at the mbit cell, the 1T1C. We looked at the sense amp. We found out the word line driver has to get to VCCP. On your project, you don't have to build a word line driver. You can just have a signal that goes to VCCP. And that works great. And that's what everybody does. That's what I ask you to do. Now the row decoder. If I've got an array that is 1024 by 1024, if I got a megabit array, I've got 1024 word lines. 10, 23 word lines on there. I'm going to have 1024 word line drivers. So I'm going to need, they're going to need to fit in whatever the width is of each row. I'm going to need to decode those lines. For 1023, I would probably have 10 address bits coming in. I'd have 2 to the 10th, which is 10 address bits. So those 10 address lines coming in have got to get translated to the 1023 different word lines. I'm going to need a decoder for that. And we'll talk about the row decoder next. And then we'll be done with chapter 2. What was this doing here? Sometimes I question it. Okay, what's the point of this? Okay, so I've got, this is a voltage translator for the low input. M4 and M3 are a latchy thingy. And this will be the technical term that I use for this from now on. It's basically to latch those signals high. This looks like the bootstrap driver we just talked about. I've got the M1 transistor here. I'm using a PMOS transistor in the top to help me out a little bit, pulling the voltage up. We want to analyze this circuit. I'm starting out with a case that my input voltage is 0 volts. We want to figure out what Vx is. Well, and what are the operating regions for each of these transistors? Okay, the gate of M1 is at VCCP because it's tied to VCCP. Gate source, Vn is 0. So this transistor is on, Vx is going to be 0 volts. Because this transistor is on, so the drain to source becomes transparent. If Vx is at 0 volts, M2 is off. It's in cutoff. Let me finish making my F. Okay, M2 is in cutoff. What else do we know here? Vy. Vx is at 0 volts. And if you follow that line up there, the gate of M3 is tied to Vx. So this is at 0 volts. I've got 0 minus VCCP on M3. So this transistor is on. Vy will be at VCCP. Yes. I'm double checking. I have the answers on my over there. So we've gotten that far. Now we've got the voltages on pretty much everything. We want to figure out what region of operation they're in. M1, its VGS is VCCP. Oh, come on, finger. Or touch screen, whatever. its VDS, drain to source, is 0. So it's in triode. Because VDS is less than VGS minus VT. So it's in triode. That's a good thing. That's saying it's a digital on. Okay, M2 is off. It's in cutoff. M3, its VGS is 0 minus VCCP. So it's not in cutoff because that's a PMOS. And its VDS is 0. So M3 is in triode. And if you want to see, you can always call up my slide solutions if you want to see a non-finger painted version of this with a little bit more detail. But you won't hear me talking on that one. The final transistor we need to look at is M4. Its gate is at VCCP. Its drain is at VCCP. So it is in cutoff. Okay. That's what's going on in that circuit when you have a low input. A lot of times when you're a PUP engineer and you're just starting out, or you're doing failure analysis or test engineering, you'll have a device that has a problem with this particular circuit, and you kind of go through and you analyze the circuit when it's on, you analyze when it's off, and you analyze, trying to figure out what those internal voltages are. You can do it with a simulator too, or you can do it with your finger paints. Either way, you're going to come up with a better idea when you do your measurements on this circuit. Oh, wait, this M4 is on. Something's wrong with M4. And then you can zero in on what the mistake is. But you have to know what you're expecting first. That's why engineers go through these kinds of activities. I'm running out of time, aren't I? Right.
No, you still have 15 minutes.
I know, but I also have like 10 slides. Okay. So now we look at this with a high input. With a high input here, the M1 is still on, M1 still in triode. This is going to be a very low impedance. I'm going to get VCC for VX. If I get VCC for VX, I turn M2 on. And I'm going to turn M3 off, because now I have a high voltage at the gate. If I turn this transistor M2 on, my voltage Y is going to go to VO low, which is going to be approximately equal to 0 volts. I put 0 volts on the gate of M4. It turns on, probably in triode, because this is digital. It turns on, and what does that mean? I've got a drop of VCC minus VCCP across here. Is that going to get pulled up? X, ultimately, yes, X will get pulled up to VCCP with this transistor turning on. Which just keeps that one off, which keeps that one back on. The on transistor will actually be in triode, and we can use those. I froze. Okay. I've frozen, Julie. The interesting thing is I went and I looked, and my Zoom is still recording my motions, but I can't see myself moving.
We can still see you moving.
I'm frozen. I've got this really weird look on my face. I'll be back in about 30 seconds.